Good morning. First of all, let me thank you and Institute for inviting me here and share some of my experience. And even though the biodata you already heard, but I would like to really specify and give importance that I am only an engineer. I am not a scientist. I have learned from scientists, so what I am going to share is only what is my learning. I am going to transfer it to you. However, on the engineering areas, surely I will be able to really give you with some authority welding, manufacturing technology, and now you must be hearing IoT 4, Industry 4.0, Industry 5.0, automation, or what we can do it manually and where to choose automation and where not to choose automation. These are really my core subject, whereas Chandrayan is very favorite to me, because I was fortunate as soon as I joined Godrej in 1987. There was an opportunity which was brought by Professor U.R. Rao, who was the chairman that time, and he decided that if ISRO keeps on doing manufacturing and management of their programs as far as getting ready with the various rockets as well as satellites and the ground systems, then the scientists will not be able to focus on future R&D. However, those thoughts were very limited, not as today, where the government of India has taken the POMA is driving private industries to come in a large way and participate in the programs of national importance. And it's not only space, but defense and nuclear and so many other areas, energy development. Everywhere the private sector encouragement has happened. But I am talking about 87, when initiative which was taken by ISRO, which was an autonomous body under PMO, to invite private industries and large industries like Walchandnagar, Larsen Toubro, Godrej, they were invited in those days. However, our understanding, you know, most of us know Godrej for locks or maybe a refrigerator or maybe cupboards or some other consumer products. But you have never heard Godrej into this kind of a specialized fabrication. So there was an opportunity for Godrej to learn. There was an opportunity for ISRO to involve industries like Godrej, who have never done into hardcore engineering. And the association was favorable in both sides. So our chairman, Mr. Navroj Godrej, he agreed to this opportunity which was given to Godrej, and we decided to start working on it. Now, you are all becoming engineers. There are professors who are sitting here. You know that when we are to lift anything up, it has to be light, it has to be strong, it has to withstand various forces, the aerodynamic forces and other things. So the selection of material is completely different than what is used in our regular day-to-day life. For example, Godrej has never made even a cupboard which is made in stainless steel. It was all carbon steel with water painting technology you can implement on it. Similarly, locks, at the most we have used brass or maybe a stainless steel lock has been attempted, but not beyond that. And all these alloys, even though they are good for our day-to-day use, they are not good for using into the space or into the rockets or satellites or ground systems. So they are very heavy. And heavy thing to lift up is not going to be easy. As I will discuss further, you will understand how difficult it is to really take even 1 ton of payload into an orbit of 1,000 kilometers. And in the Chandrayan, the subsequent section when I will talk about, we are going to travel a distance of 3,84,000 kilometers. So even 1 ton, that is 1,000 kg into 1,000 kilometer orbit, if we have to take it, the cost of taking 1 kilogram is more than $15,000 per kg. So that's the efforts which are required to be taken, and it's everything revolving around the weight. It's revolving around the various conditions in which the rocket is going to pass through, starting from the ground where it has to take off and go to almost absolute zero. We are not going to achieve minus 273, but minus 265, 266 is the temperature the rocket and satellite is going to see. Almost going to from 1 bar pressure where we are currently talking, to absolute vacuum. I mean, it will not be real zero, but 10 raised to minus 11, minus 12. Those of you who are familiar with this technology, numbers and the terminology will understand. It's difficult. And plus, there are various forces which are acting on it. First, the gravitational force, you know it. As we are going, aircraft also, you will see that it bumps because of, it has such a large wings. Almost the length and the width of the wings is similar. For a normal aircraft, for a fighter aircraft like a cycle, it is reduced. So all these challenges are required to be taken. That means the strength required is going to be similar to what we are experiencing at ground, but at the same time, when we are going to go up, the weight has to be reduced. Our aim is to take maximum payload. If I take efforts and a PSLV, GSLV which weighs about 200 tons to 400 tons, the rocket can carry as on date the highest capability what we have is GSLV Mark II, or now it is called as the LMV-3, which has used in this Chandrayan 3 project. Can take around 2 tons very safely, but up to 4 tons, and that is how what has been attempted in this particular Chandrayan 3. We have carried a weight of 3,850 kilograms first into a transfer orbit, that is somewhere between 270 on apogee and perigee was something like 36,000 or something, and then it got improved. We'll come to that later on. But what I wanted to emphasize on you is that this particular activity going into space or defense, whether it is an aircraft, fighter jet, helicopter, missile, UAV, drone, everything has to be as light as possible but as strong as possible, and should have the least consumption of the fuel. We don't have petrol pumps so far into the orbit where the fuel what the satellite is going to carry gets exhausted, we cannot refill it. And that's one of the aim of having a space station where we can go park our vehicle there, get the refueling done, then go another distance, go to moon. Once again, there will be a refueling station, fuel it, go to Mars, go another. So like that, the idea is that we can go on jumping and carrying our satellite from one planet to other planet. And right now we are also talking about going towards sun. We have a project like Aditya where we will be going as close as possible. Going on to sun so far looks to be difficult, but maybe 40 years back going on moon was also difficult. So another 40 years we may be able to find out a material which can withstand the temperatures on the sun, and we can land on sun also. We don't know, but that's a possibility. So that brought me to this new material. So in aerospace we use aluminium, titanium, Inconel and various grades of alloys, these alloys, and also a lot of material technology like composites, carbon fiber, Kevlar fiber, ceramic fiber, all these technologies are coming in. And I showed some interest in developing those material characterization and studies on that. I mean, you will really laugh that I have been passed out from IIT in '83, learned a lot about titanium and these exotic alloys. Columbium based alloys are there, then we have cobalt based alloys which can withstand very high temperatures. There are many alloys which has a tungsten in it. But I never got an opportunity to physically see that. Even in metallurgy in IIT also I was not able to get an opportunity to see these alloys. It's only when we signed up a contract with ISRO and DRDO, Indian Space Organization and Defense Research Organization, then first time the titanium piece was given. So I told my colleagues also that time, I have studied everything, I know about this material, everything, right from how it is mined and refined and purified and processed and finally brought to a shape of a tube or a sheet or a plate or a forging. But there was no opportunity. Even a small piece of titanium is so expensive that IIT probably was not able to afford it. Today, of course, we have lot many alloys. I am talking about 78 to 83. So those days, these alloys were not there. And the same was the situation of ISRO. When they brought all these scientists together and developed this VSSC Vikram Sarabhai Space Center or Liquid Propulsion Center, or now we have a launch pad at Shar near Andhra Pradesh, Sriharikota. So all these centers had no literally facilities. I had an opportunity first time to visit ISRO in 91. 87, even though we signed, we were not allowed because secrecy was important. But when we signed an important project of developing a liquid engine, which is used in this Chandrayan, also called as a Vikas engine, there was a requirement by European Space Agency that they wanted to develop a particular type of a engine for their own rocket. They had a lot of money, they had a lot of resources, labs, but as you know that there is a limitation of manpower in these European countries. So they appealed to Government of India that why can't your scientists come stay there with us for 4 years, 5 years, 6 years, whatever time it requires, and let's jointly put an effort and develop this Vikas engine technology. They call that as a Viking engine. We call that as a Vikas engine. And then these two teams of the European scientists under ESA and Indian scientists under ISRO, they worked together. A lot of scientists were deputed to various places in France and Germany and Spain and UK. And others were working, supporting from India, and similar thing happening there. And finally the Vikas engine got developed. Now, as a respect to the contribution which was done by Indian scientists there, the European agency agreed that you can carry the drawings, what has been developed, but you cannot carry any manufacturing technology. Only the drawings were given to us. But that was also a great help, because to do all these things, there are a lot of constants. Even on Chandrayan, obvious question for you will be that ISRO had almost a success everywhere. Chandrayan 1 was successful. We were able to take a satellite, orbit it around the moon. We detected for the first time that there is a possibility of water on moon, which no other country, the other 3 countries or 5 countries have gone near the moon. They are not able to detect it. But our Chandrayan 2 was not successful. We went right very close to almost 100 meters or so, and finally we got a shock on the TV, when you probably have seen, or if you see on YouTube also, those old films are available. It crashed. So what happened between that 100 meters to reaching up to the moon? And why did we fail when we have a history of success in every where we failed in this? So what happens is that since it is all imagination, there are many assumptions which are required to be done. And the countries who have successfully done that, the Russia and the US, they were the first ones to really start the competition who will go first onto the moon. But they never shared. All the European, Americans or Russians, the 3 of the important agencies who are doing work on it. Today European agency is far behind us. They have not even thought of going to moon or making all the things what we are doing it today. Americans and Russians are still going. China is coming up very fast, and they have picked up a lot of it. So we are the 4th country after US, Russia, China, and now India, who is really talking in a very authoritative way. And we have generated a lot of our own data. Now, obviously, like other 3 countries are not sharing, we will also not share any of this specific data. All the assumptions are required to be revalidated. And simulation also you can do it. Now latest generation computers, you have very good simulation capabilities. But if your assumptions are wrong, then the simulation also will be wrong. It is like garbage in, garbage out. So if you do something wrong in the giving instructions to that simulation package, your output also is going to be wrong. But I think now we have a good understanding of what has gone wrong, even though the mission, part of the mission, orbiter of course is running today also. Chandrayan 2 orbiter is available, and it is giving a lot of help to Chandrayan 3. So as an overall mission, it was only 30-40% maybe unsuccessful. But that last 100 meter, our sensors were working, even though it crashed. And they have captured all the data which is required. How much is the gravitational force, what was the pressure, what is the temperature, how the overall things are going to react when we are going to land there. So the chances are good. So what I was saying is that since it has a lot of assumptions, when the drawings came up from the European agency to us, how do we manufacture that? What kind of a technology is required? Titanium, Inconel, cobalt-based alloys, nickel-based alloys, columbium-based alloys, they are not very easy to work. They have very good properties, but they are not easy to work. It's only a limited zone in which you can form it, only in a limited zone in which you can machine it, only in a limited zone you can weld it or test it or give a protective layers. Like aluminum we give anodization, or on our steel we give chrome plating, nickel plating, cadmium plating, zinc plating for various applications. These alloys, they are not easy to give a protective layer, and everything which gets fabricated will undergo some changes in the surface as well as the internal. So it has to be restored back. So what kind of a heat treatments we can decide? Like steel, when we want to use it like a knife, we harden it. The same steel, when we want to use it for our car body, it has to have a good formability. So we make it to form, so we anneal it. So like that, what are the heat treatments, what are all the surface treatments, what are the different forming, welding, machining technologies? Will the inserts or HSS or cobalt based our cutting tools will work on these exotic alloys? So it was all new for us, because there was no other product except for the chemical industry which was using heavily a pure titanium, not a alloyed titanium. So once again there was a limitation. So the first thing what ISRO did is to bring all these industries together, not only those who are going to fabricate like Godrej, but the machine tool industry, the cutting tool industry, all those consumable manufacturing industries. Separate different oils are required if you want to form this, separate powders are required to be done it. Maybe ordinary grease doesn't work, molybdenum grease or high technology grease are required when you are going to lubricate this. All these pumps, the bearings which we are running it today, under normal conditions we run it for 2000 ampere, 5000 ampere, 6000 ampere. But most of the pumps which are required in the space, they have to be run at 32,000 RPM. So now from 2000, 5000 RPM to 32,000 RPM, your bearing also design will change. The material for construction for bearing also will change. It may require additional cooling also. So the whole complexity, having a set of design saying that you use this bearing or use this material or you use this shape or use this particular tolerance, from there to reaching up to the actual product, that itself was a big task. And we struggled for almost 6-7 years to make first components before we start making the assembly and testing it. The components were difficult to make it. But finally, since a national level team was formed, more than 22 industries participated from these various sectors, and we all sat together. Bangalore was our main hub where we were sitting and discussing over months together. But finally, there was one directive which was given by Professor U.R. Rao, that don't ask me to go and request European agency to give us a manufacturing technology, because that is the end of ISRO. First of all, we have been benefited by getting a drawing. Now if we also go and get the manufacturing technology, that means henceforth we will not be able to think. So our thinking process has to get ignited. And later on, when I worked with Dr. Kalam also, same thing was saying, that we should not, we all Indians are very capable of thinking, innovating. It's only a time which is required, it's only the money which is required, it's only somebody who should be able to absorb our setbacks. If that kind of a 3 structures we build in India, I think we will be able to develop it. And that's what now we are demonstrating to the world. Whether it is Atmanirbhar scheme for domestic, where we were importing all our defense systems. Today we are the exporters of defense system, and by 2030, what we are importing will be exporting more than that, which has not happened in the last 75 years. The things are changing rapidly, and that is where I think today also, fortunately 14th of August, it is going into a very close orbit from where the Chandrayan is going to look into the surface of the moon, what has been already mapped. Once again it is going to map it. And you also know that our Chandrayan is little different. Everybody has gone to the North Pole where there is a good sun available, whereas we are going for the first time. We are the first country to go on to the south side of the moon and land there, and that is where our rover can work only for 14 days, which is 1 day on moon. When we have 14 days on earth, it's 1 day on moon. And once again, when it will go for 14 days night, there will not be a solar energy available and all our systems will stop. So that's why it has limited. But we have taken that conscious decision to go and land there on south side. So like this, the innovation has started coming in, a lot of thinking has started coming in, and as a result, in 1996, on 1st January, Godrej delivered the first completely built from component level to fully assembled Vikas engine to ISRO. And near Kanyakumari, there is a place called as a Mahendragiri. It's into very deep hills, far away from any establishment. These engines have a test facility where we produce this hydrazine-based fuel, nitrous oxide kind of oxidizer, or liquid hydrogen, liquid oxygen, which is used in cryogenic. A similar technology or similar model was later on copied in 93 onwards. As we started seeing success, we started talking to Russia, and the cryogenic engine technology also was partially actually it was completely agreed, because we took longer time. The decision was ISRO that let's see how any other country's technology will look like. And 91 we signed a contract along with the Glowcosmos of Russia. That time it was USSR, to get the cryogenic engine technology. And the cryogenic engine technology was completely a different ball game, because there we are going to store liquid hydrogen at minus 260, liquid oxygen as 180 or 190 degrees centigrade minus, and both when they combine together, it is going to give a huge energy, and that will take for a very long time. The Vikas engine or any solid engine has a life, even though we take 6 to 8 months for manufacturing, and before that the raw materials and everything. The life of Vikas engine on the actual flight is 2 minutes or 2.5 minutes. Maximum we can stretch it to 3 minutes. So 7-8 months of efforts, finally your life of the engine is only 3 minutes. Such is the criticality of this space requirements. Cryogenic engine has little better, it can go to 15 minutes or 20 minutes. When we are talking about traveling a long distance, the engine should have a longer life. The solid engines which are built by Walchandnagar Industries and L&T, that also has a life of 2 minutes to 3 minutes. They can develop a huge thrust, 200 tons, 300 tons of thrust, but life is limited. And such a long distance when we have to travel, we have a limitation. So what happens is, the Americans can take their satellite to moon in 5 days, whereas we are going to see when we launched it and when we are likely to land, we are going to take about 30-35 days to travel such a long distance, because we don't have still a very large rocket, a large engine which can take a higher payload with extra fuel, and so a different technology has been used. That's also another innovation what ISRO has brought in. We are not actually powering. Once we launched out of our LMV-3 rocket, the satellite has been used very sparsely for this particular firing. We are not going to consume this particular fuel completely, because we have a limited fuel. We could take only 3.8 tons of satellite. Of that 3.8 tons of satellite, there are mandatory payloads. There are sensors, because without that we will not be able to maneuver this satellite, communicate with the satellite. After the rover reaches there on the moon, whatever data it is going to collect, the rover is not going to come back. So all the data what it is going to have, it has to be communicated back to us from it. So large number of equipments are required only for ease of logistics. It is not actually going to contribute into analyzing what the moon looks like. But those are required. So similarly, the fuel is required for maneuvering. The solar energy which is going to be used, that will be converting into electrical energy for communication. But the rover is going to move across 14 days, it is going to move onto the surface of the moon, so it requires a fuel. So there has to be a proper like we have a tolerance stacking, so similarly 3.8 tons has to be given, so everybody fights there. The communication system says that of that 3.8 tons, I want 200 kgs, 500 kgs, otherwise I will not be able to do the communication. The payload carrying, actually the one which is going to see a camera, or there are sensors, or there are some experiments our rover is going to do it. So those people have said that we want another 600, 700 kgs, otherwise we will not be able to put in. Then the solar panel, that has a weight of about 100, 150 kgs. So like that, when the complete tolerance stacking, we do it, the weight stacking has been done, it's a big competition to put everything into 3.8 kilograms of the satellite. So we have another program called as a semi-cryo, which is going to develop second largest booster in the world. 200 tons capacity booster is under development. It may take another 3-4 years. But after that, we'll have a payload carrying capacity going from 4 tons to 8 tons. And then more payload will be able to take it onto the satellite or onto the rover or the lander, which is going to go onto the moon or various other missions which are going to come. So I'm shuffling between two. I'm deliberately not using a PowerPoint presentation. You can stop me anytime. There is no proper sequence or something which I thought. But before going to Chandrayan-3, I just wanted to give you what exactly the ISRO does, what difficulties it has gone through, and after overcoming all these difficulties, only today we are so comfortable and talking about landing onto the moon, and why we are only the 4th nation, why other nations, even the Japan is trying, Korea is trying, Israel is trying. There are many countries, I mean I can name almost 21 countries who are trying efforts to, may not be a launch vehicle, they may launch it from Indian launch vehicles, rockets, or European rockets, or American rockets, or Russian rockets. But maneuvering satellite and taking it to such a long distance, that itself is a big issue. So similarly, I can talk about the cryogenic engine technology, how we brought it from Russia and how we did into it. But considering our main focus on Chandrayan, let me just summarize what I just said, just for ease of our understanding. So there are mainly 3 major important factors for any mission which ISRO or even a defense missile or helicopter or aircraft has to take it. First is how to overcome an inertia. How do we lift what is resting onto our earth? So that requires a huge force to first take it up. Once you lift up even by 1 millimeter and your rocket is now hanging in the air, currently it is situated and it is sitting onto the launch vehicle, on the launch platform, and it has all the umbilical coils and everything is fed through the ground systems. It is not using anything internally, even though everything is ready. But when you have actually the firing time, T minus 3 seconds, the engines will start burning. Even though 3 seconds the engines are burning, it cannot take off. It has to develop that thrust. No engine can develop thrust on 0 second. It takes some time to reach up to the peak, and then the full thrust is developed. When the full thrust is developed, you will see a little lift off. And that lift off is most important. The lift off has to be exactly perpendicular to where we have a launch pad. If it is at any inclination, any angle, it may turn the entire rocket and topple it. Because L by D ratio, do you know what is the height of a rocket and what is the diameter? The diameter is roughly 4 meters, 3.8 meters, or there are some stages in between where it comes down to even 2.8 meters. But the length of the rocket is almost 60 meters or 70 meters. So just imagine what is the L by D ratio. You understand L by D ratio? 60 divided by 3. 20 times. A stable structure, we consider that 3, 4, 5 is a stable structure. We can manipulate up to 8 or 9. But here we are going to take 20 times length to the diameter ratio, and it has to get supported. So that's the first challenge. How do we lift off? How do we move up by even 1 millimeter, 2 millimeter and make the rocket to stand straight? Then comes the second. Now it has already overcome the inertia, come into the air. How do we maneuver it? How do we take it to the required destination? Like we use GPS, there are also GPS which are to be developed by every ISRO kind of R&D organization. There is no standard GPS which comes in our mobile free when we buy a mobile. You have to decide a path. How do we want to take it? Then should we go from the polar side? Should we go from the equator side? Should we go directly onto the moon? Even though we see moon over there right now when we are launching, by the time we are going to cover a distance, moon has moved, Earth also has moved. So how the relative distance is going to change? How are we going to track that? And if we miss even by 10 kilometers, suppose this speaker over here is a moon and I am just moving, even if it goes, a missile, or even if the satellite goes like this, which doesn't come into the gravitational force of a moon, then it is going to pass through. Once you pass through, then you cannot bring it back. It's a huge effort to turn the satellite or a yarn or something and bring it. So after traveling such a long distance, you have to come exactly to the center of the moon. And that is what is being done. You cannot go exactly in the center. So what you do, you go first, orbit it, find out which is the best way to go near to it. And today on the 14th, as he just read out, is an important day because we have transited successfully from after the liftoff. Satellite has been ejected out. It first came out of the Earth's gravitational force, then it entered into the moon's gravitational force. This transition also is very, very critical, very important, because even 1 degree mismatch in what has been planned into the trajectory, you are going to go not on moon but somewhere else only. And recovering that is a huge effort, so you have to spend a lot of fuel. And you may recover and come back onto the moon after all these things. But by the time you land onto the moon, your petrol or diesel, I'm just giving simplification, it's not petrol and diesel which goes there, that will be over. So you will not be able to move further then. So the trajectory cannot go even 1 degree from what has been decided. So that's the second challenge, that how do we really plan? And that is where I think we Indians scored it far, far better, and our rocket, even though it is going to take our yarn, going to take 30 days or 35 days, it is going to go precisely. All our attempts, whether on Mars or moon, that has never been missed out. Whatever is planned, exactly we are able to do it, because I think we are very strong on astronomy. पंचांग आपण करतो ना, आपलं पंचांग किती जुनं आहे, इतके वर्षांपासून आपण पंचांग बनवतोय. आपल्याला ते बरोबर ग्रहांची movement, how they are going to happen, what kind of a force they are going to exert on Earth, what kind of a force they are going to on our own body. We have understood it so well that we cannot miss in that. And all our other scientists from different nations, they are after us that please explain how so many years back you developed this panchang and how it is really coming even true today. So that's the second important technology which is required as to how to maneuver and go to the right destination or a right spot. A low Earth orbit satellite which goes to 500 kilometers to 1000 kilometers, which looks to be very close, but there are so many satellites. It's like, bumper to bumper, it has come to almost that stage. Every country has been successful in launching a satellite in this orbit. So you have to really select which orbit you want to do it, you have to find out a right spot, and you have to go and launch it there and keep your satellite in that spot only. Otherwise the two satellites will collide. There is a lot of debris. So if something you notice it, you have to maneuver it. So launch vehicle as well as satellites, when you are taking it from Earth to outside Earth's orbit, every hurdle is going to come, like we have a speed breaker, we have somebody else coming up, or any two-wheeler coming and suddenly coming in front of you, or a cow or a buffalo coming onto it. Exactly same thing. I am not exaggerating. If you really see on YouTube some of the videos, they are simulated, some of them are real, where they have put a camera and seen that how the debris is coming and the satellite has to maneuver its path. It has to take a different path. And that is where we were not able to give whether 23rd or 24th of August when we are going to land. And that's now going to decide today, after we come into that 200 kilometer orbit near the moon, we will be able to precisely decide when we will be able to land, which is the right location where we will be landing it, and at what time we will be landing on 23rd or 24th. To that extent, today evening when that maneuvering will happen and we will go into that 200 kilometer orbit, we will be able to do all the scans which are required, calculate it back, and then plan for the exact time, like a launch vehicle, exact time. very rarely you will see a computer will detect some flaw and then it gets delayed. The window available to launch is hardly 5 minutes to maximum 30 minutes. And if you miss that window, then sometimes you may have to wait. If it is a low Earth orbit, a week or something, you have to wait for getting the next window. If it is a geosynchronized, where we use our mobile technology, that is 36,000 kilometers away, there you have to wait for 15 days to a month. And moon like a mission, you have to many times wait 3 to 4 months. Had we missed this slot to launch, we would have to wait, even though everything is ready, another 3 to 4 months to get a next slot, which is the shortest distance where moon and earth can come together, or by the time our satellite goes, don't have to travel a long distance. So that's the second. Lot of planning is required to decide on when to launch, how to launch, what trajectory, what path it has to follow. Now communication, when we are deciding this particular thing, we have to keep on checking whether it is at the right location. So on television, when we hear live telecast, especially on the news channels, you will see that when there is a little remote areas when our reporters are going, the anchor on the studio, he is able to talk to us, or we are able to hear anchor immediately. But the same anchor, when he has to reach up to his reporter at a remote place, we see that nothing happening. After he has completed his sentence, the other person is only nodding his head, because he has not completely heard that the transfer of data has not happened. It takes 1 second, 2 seconds, 3 seconds to reach up to him, and then he communicates, so which also takes another 1 or 2. So even though he is speaking, we don't able to do it. So there is a delay of 2 seconds or 3 seconds after the anchor has completed his question to get the answer from him or the reply from him. The same thing happens as we go further and further. So for here to moon and from moon to back a signal, it takes about 6 to 7 seconds. Now 6 to 7 seconds and the velocity at which we are traveling. Do you know what is the velocity at which the rocket is? Obviously when it takes off, it is zero velocity. As it goes little up, maybe goes to our 100 kilometers, 50 kilometers, 60 kilometers like a car. But finally when it has to come out of the Earth's orbit, it has to have minimum 8 to 9 kilometers per. Do you know what is the denominator there? 8 to 9 kilometers per hour, minute, seconds. 8 seconds. 8 to 9 kilometers per second. So imagine what is the speed at which it is going. And if there is a delay of 6 seconds for us to get a signal or to react back, if the launch vehicle or the satellite sends that I have changed my trajectory, I am not on what you have asked me, so what should I do? So the signal is coming 3 seconds. Another 3 seconds for us to communicate back, even if we are ready with the answer. First we need to analyze whether he has gone left, right, north, south, up, bottom, and then accordingly we have to give a signal that which thruster on the satellite or on the launch vehicle has to get fired. Suppose we take another 3 seconds to do that. So 3 seconds for getting a signal, 3 seconds for us to process, and 3 seconds to give back the signal to it. In 9 seconds, it is no more there where it was actually there. 9 seconds at, let's say for ease of simplicity, 10 kilometers per second, it has already moved 90 kilometers away from where we got a signal. Now that 90 kilometers, has it gone into the right direction in which we wanted, or it has gone into another direction? So if we say and give a command, and if it has gone to the other direction, at the most he will come back to 0. The correction will not happen. 0 means what deferment when the original signal came in. So it's very difficult to communicate. So onboard controls on the launch vehicle or on the satellite are also very, very critical, very important. And that is where the AI, now what we talk AI, ISRO has been doing it for last so many years. You have to give the minimum, like we give a first aid, you have to give the first aid to the satellite or first aid to the launch vehicle. On the spot it should be able to detect and decide whether it has drifted north, south, up, down, whether its altitude has come down or whether it has moved towards polar or it has moved towards equator or it has come down to a completely different direction, east or west. So that initial understanding and decision making has to happen on board itself, so that this 9 seconds delay will be able to minimize it. So a logic which is required, and that is where a lot of thinking. Number of scientists are just sitting like this and thinking as to what could go wrong. In engineering also, in manufacturing also, we have this particular technology, foolproofing. What one can make a mistake, and how do I stop that mistake? And if that mistake has to be stopped, how do I make a jig, fixture, or some kind of a sensor, so that it will immediately alert him there before a supervisor or a manager notices it. So exactly same logic is being followed in this. So that's the second area where ISRO does a lot of expertise and ideas, and creates various programs and artificial intelligence and dumps it onto it. Now we have traveled, we are able to track correctly after liftoff. The satellite has been launched. It means whatever the launch vehicle has to do its job, that has been done. Now satellite is into the orbit. So when it is in orbit, still it is under gravitational force. So what keeps it there now? If it is under gravitational force, why the satellite like a ball doesn't come back onto the earth? It is this speed which is giving the centrifugal force. If you take a small weight and tie up with a thread and start rotating, only at certain speed only it is going to stay there. Otherwise, if you reduce your speed, either the inclination will come down or finally it will stop. It will come and hang vertically as the gravity is going to work on it. So the speed is required. The speed, once it is imparted, has to be maintained. Speed cannot be reduced. Once the speed reduced, it will start coming down to the earth. If you increase the speed, it is going to go out of it, like a centrifugal force. So this combination is required. The second portion of this trajectory mapping is how do we do an adjustment between this speed and the gravity. So first we launched, if you have seen, on 23rd of July, when this particular launch vehicle launched it after 15 minutes. It launched into an orbit of 270 kilometers on one side and almost 36,000, 34,000 kilometers on the other side. Don't go on to the numbers. Numbers may be here and there wrong. Numbers are not important. So I am not really going to challenge myself, or don't challenge me that no, it was not 34,000, it was 38,000. It's okay. I mean, understand is important that one side it was around 200, other side it was 36,000. That's the orbit any object takes up. It's a physics. Next time when we'll talk about that physics also, as to why we cannot put a satellite into a perfect circle in the first attempt itself, why it has to keep on overcoming that particular orbit. So once this happens, then we have to start maneuvering that orbit and increase it to the extent possible. And then there will be a stage where you consider that here there is a Earth, a moon, and this satellite has started going, orbiting. Finally a stage will come between the two where there will be a balance. The Earth's gravitational force and the moon's gravitational force will be almost equal. Now we all know that moon's gravitational force is 1/6. Whatever is our weight here, we will be measuring 1/6 of that on the moon. Size of Earth is also quite large. Size of moon is, as compared to Earth, is very small. I think some 1:9 ratio or something is there in the diameter. Now in the same proportion, as you go near to the moon, away from the Earth, there will be a point, maybe 1:9 ratio. Once again the physics will explain why that 1:9 ratio, the distance. That means 384,000 kilometers if you do 1/9 or 8/9. That's the point where this transition is going to happen, where it can go either towards Earth because of the Earth's force, or it can go towards moon. Till the time it is the Earth who is dominating, and once this 8/9 distance is covered, it is the moon who is going to dominate the gravitational force. Now, as long as you are going away from Earth, you are accelerating. When we are accelerating, when we are climbing up, it's easy for us to climb up. When we are accelerating, it's easy for us to control our vehicle. But when we are braking, then it becomes difficult. When we are climbing down, it becomes difficult. You cannot have control over yourself. It may be like a free fall. You are climbing down and you miss a particular stone or a step which you wanted to take it, and you slip, you are surely going to fall. But if you are going up and if you miss a step or a stone slips below you, you can still hold your hands and control it. Same thing happens there. You cannot have a control when you are moving from acceleration phase to a deceleration phase. When you are braking yourself, once again a different level of expertise is required to be brought in. We cannot afford to have a free fall. All these engines are firing all this time, continuously or whenever it was required. But now the engines are going to fire exactly in the reverse direction. We want to go slowly into it, so brake kind of a engine is used, the direction is little changed, and then slowly we are entering into the moon's orbit. Once again, we cannot enter into a perfect circular orbit. It has to have an elliptical orbit. As I said, we can discuss it later on. But same way, as we have come out from the earth and traveled that distance and went there, we will be entering into same elliptical and slowly start reducing up to 200. Now 200 to actually landing. So from today, 14th in the evening, whatever 11:50, 12 o'clock, the maneuvering will happen and we'll go into a perfect 200 kilometers orbit. To go onto the moon's surface, we are going to go very slowly, very gradually. There is no hurry, because we don't have that kind of a powerful engines, and even if we have a powerful engines, we don't have that kind of a fuel. When you are going to actually brake it, you are going to consume lot of fuel. You know our nowadays that we have a dual vehicles, I am forgetting, hybrid vehicles, where we brake it, our battery gets charged. So much of energy gets generated when we are braking. But when it is generating, that much energy is being applied also. And same thing, our satellite or the yarn is going to apply that kind of a energy, and we have a limited store of energy. We cannot carry infinite capacity of energy. Energy is heavy. 1 kg of the hydrogen fuel what we are kging, 1 liter of hydrogen fuel is actually 1.6. It is heavier than water. Water is 1 liter is 1 kg, but when you are talking about nitrous oxide, when you are talking about hydrogen based fuels, they are all heavy, heavier than water. And that is where they are giving this so much of energy to our systems. So once that happens, we will be able to then slowly detect what distance we have gone, how much we have gone it, and then finally going to land it there. So that is the second technology which we are going to use it. Now the third technology is, the distance is so large, how do we put a signal? If we want to ask that today I see that you have a good sunshine there, or you are having some hip or some crevice or some valley or something, and your path needs to be changed, even though it has its own autonomous sensors, but we want to do some other experiments as we see there what we have not seen earlier, then how do we communicate? And we are able to put a signal. The signal what we are using it today, you see, I mean, we are just coming and we are discussing on the way that whether Vodafone is giving a better signal or Airtel is giving a better signal or Jio is giving a better signal. Now all that depends upon how many you have seen those towers which they put. If you have more towers, you will have a better communication, a better signal reaching up to there. Now we don't have any tower in between Earth and Moon. We don't have our own space station. Even if the space station is there, it is only 800 or 1000 kilometers. Now 3,84,000 kilometers when we are talking, even if a space station gives us additional antenna there, in Earth or a space station, 1000 kilometers in 3,84,000, it makes no difference. It will not help anything. So then how do we communicate? So the third challenge for ISRO was to how to establish the antennas, the radars that will be placed on Earth, but will still be able to communicate to the satellite there or the yarn on the moon. And whatever signal or whatever data the yarn has captured, here we can put plenty of energy.
I will explain you how we put that plenty of energy and what kind of RF frequencies are used to communicate and transfer this data or signal to moon. But on moon, first of all, we are fighting for having its own survival there. How do we generate so much of solar power so that we will be able to communicate back that signal to us? If the signal is not powerful, how do we reach 3,84,000 kilometers and still without getting any dilution or some miss out? When we transfer data from one computer to other computer, there are many times we see that data is not completely transferred. Some error takes place. Now that kind of a small error also is going to make a huge difference. So data has to be perfectly transferred. So then the ground systems were developed. There is a ISTRAC, a separate cell of ISRO, which thinks on all these things, and we have built near Bangalore, about 80 kilometers from Bangalore, one of the largest antenna in the world. I mean, there is 34 meters, ours is 30-meter diameter. Now you see our small dish antenna, what we put for our TV channels, that itself in rainy season or when there is a wind or when there is a small kind of a cyclone or something, it comes out. That is not even half a meter. Now we are talking about 30-meter antenna. That has to be manual. It cannot be stationary. All our antennas are stationary because our satellite is stationary. Satellite is geosynchronized. When we are talking about 800 kilometers, the satellite goes on Earth only 5 times in a day. That's the frequency or the revolutions it is going to carry. 5 revolutions in a day. And 5 revolutions, it means from east horizon to west horizon, you get about 30-35 minutes only. Your antenna has to be focusing like our solar. If you want to really capture maximum rays of solar, most of us, we keep the solar panels north-south facing. Southeast facing. But that gives only 60% efficiency. If you want to have really 100% solar energy to be captured, your solar cell, if you try to move as the sun is moving, then you will get all the maximum opportunity of a solar rays to be captured into your solar cells and take it into your charging batteries or heating water or other usage what you are going to do it. Now here launch vehicle is moving, satellite is moving, moon is moving. Every day moon doesn't come at the same location. It comes but at different times. So your antennas are to be required to be programmed. They should be able to maneuver. A 30-meter antenna has to be maneuvered to that accuracy of how the satellite is going to move without losing. Because if you don't have eye-to-eye contact straight, once again you are going to lose energy. Rays are going to come straight, but you are going to miss. Your antenna is 30 meter, even though it's huge, but from 3,84,000 kilometers the rays are going to come up. Even if it is going to travel in a right single direction like a laser, doesn't change direction even if it goes kilometers and kilometers. So same rays are used which doesn't change their direction, doesn't get impacted with any of the wind velocities or other gravitational forces or other forces which are acting in the space. Still moon where we have landed and where we have a satellite or the antenna has to be perfectly, it cannot be little inclined, all the rays will go away into a wrong direction. The intensity of the rays which is required will not come. So that's the third challenge what ISRO had. So we have built a large antenna. We are giving almost 100 megawatt energy into that antenna for passing a signal. The signal at the earth is so powerful that by the time it will go up to the moon, it will go without any loss of any data or without loss anything and reach the moon surface safely. But now 100 megawatt energy, how do we create? Can solar energy create 100 megawatt energy? It's not possible. So exactly reverse is being done. Whatever best power we are able to generate it there onto the moon with the whatever best solar antennas and whatever generators we can carry with the limited weight carrying capacity. So we are able to generate about 10 kilowatt. Here I am talking about 100 megawatt, and now a signal on the moon is going to be 10 kilowatt. Now 10 kilowatt also is not available all the time. It takes the solar panels to charge the battery. Solar panels doesn't generate 10 kilowatt. It has to charge battery, and then there will be an inverter or something which will boost the voltage and generate extra energy. So it comes in impulse. It doesn't come continuously. So all your data you have to connect in such a way that it will come into different impulse, and all those impulse, when they are received here on the earth, you have to once again tie up all those small jigsaw puzzle, or like an elephant. First you will get only your trunk, and then you will get ears, and then you will get legs, and then you have to patch up everything correctly and see what has been coming here. So data processing, data analyzing is also another very large big challenge. So after all these things, if we then decide a moon mission or any mission, then comes the next challenge. Who is going to fund it? One mission is about 600 crores. The mission itself. That means that day what we are going to spend. But all the efforts, all these test facilities, simulations, 6 to 8 years of efforts which are required. If you count all that together into a mission, it's no more 600, 800 crores of a mission. It goes to 3,000, 4,000 crores or even more. I mean, it all depends upon how much experimentation you have done, how much simulations you have done, how many scientists you have put deployed onto it, what kind of a time duration you want to do it. If you want to do it over 100 years, okay, you keep on spending 2 crores every year, it's okay. But if you have an ambitious plan to do it in 3 years, 4 years, 5 years, then those many engineers, those many industries, those many other technologists, scientists, academia, everybody is required to be involved into it. So how to bring that kind of a money? And then the debate happens, should India spend money on going on to a moon, or should we educate or create more better roads or other better living conditions for our human beings or the Indians? And then finally the budget is allocated. Now how do we use that budget effectively? Every establishment requires almost 30-35% of their current budget. ISRO has a budget of about 10,000 crores. But of that 30%, 3,000 crores is required to maintain and keep running their existing facilities. All these facilities once created, whether you are going to use it today, tomorrow, after 3 years, every day you have to do some activities, then only it is maintained. You cannot shut down that facility and start it after 3 years when you require. So you have to keep on doing some firing, some testing, some other simulations in that facility. So that requires 30%. 30 to 40% goes into the salaries and wages and other contract people who are being used. So of that 10,000 crores, finally actually what is being put and deployed towards the fundamental research is only the balance 40% or something like that. So even though 10,000 crores look to be a big sum, everything doesn't go to the fundamental research. And that is where we have to really do a frugal engineering. We have to do some different ideas, innovations, use our old history, our culture, and find out how do we do it. थोड़ा पानी मिलेगा? Oh, sorry. So after overcoming all these issues which I explained to you in 3 ways, then only we are ready. Then the money comes in, then the deployment of manpower comes in. You have now money, about 3,000, 4,000 crores money to be given to the scientists, but who are ready to come into these areas. Because ISRO is the only organization. If you don't like that organization for whatever reasons, you have no other choice and no other option to go. If I am working in auto industry, if Tata is not there, Mahindra is there, Hyundai is there, Bajaj is there, so many other opportunities are there. Here there is no other opportunity. So you have to then keep on doing the work with ISRO only. So like that there are a lot of other constraints also. I just wanted to give an idea of, it's not only easy to bring money, but to keep scientists motivated, to engage scientists, engage academia, engage private industries. We spent our first rupee on ISRO way back in 1987. Then in 2004 I was given opportunity to start heading this division. Till the time our turnover for Godrej, a large company, we are the major contributors of ISRO, the third on their list our turnover was 5 crores. We had more than 1,000 people working in this, because there are so much of technology, so many things are required. Even if you have a work or no, your expertise, your qualifications, your attestation has to be maintained over a period of time. We were producing Vikas engines when we started producing only 1 in 3 years. That was because we had no launch vehicle to really fly that. Now the situation has changed. We are producing 20 to 25 Vikas engines every year. We are producing about 10 cryogenic engines. We are developing semi-cryo. We have another higher thrust cryogenic engine. So overall we are doing about 40 to 50 liquid engines today for ISRO. But 87 we spent first money. I am not saying first money 1 rupee. It was some 3 crores or 4 crores we spent in 87. 2004 when I took over as a division head for this, we were in loss. It took me another 10 years. 2014 first time we saw profit. And the same thing is there with L&T, same thing is there with Valchandnagar, same thing is there with all other industries who are working with ISRO. It takes time. It takes very long time. So unless and until you have that kind of a vision, what Homi Bhabha and Vikram Sarabhai brought it for the nation. So similarly, every person, why I am giving you all this is what I am talking about the ISRO, what I am talking about industry. Same thing happened with every scientist. He comes out with a brilliant idea, but to prove that idea and implement it, it takes 20 years. So half of his career just goes away in only thinking and creating the facility. The second half, or the next generation which takes over, they may be successful. So you have to really have that kind of a huge patience to see a success. And after that only we can plan for this kind of missions. So I will take a break, not for I am tired, but I think I gave a lot of information to you in this short time. If you have any questions, if you have any queries, and then we'll come very specifically to first Chandrayan 1, Chandrayan 2 and Chandrayan 3. So that's what I am planning, if that is okay. I'm open for any questions or any suggestions or anything if you have. There must be Chandrayan 1 and 2. So some of you also have studied, understood what we attempted in Chandrayan 1 and Chandrayan 2. Now these missions, when we planned, especially the Chandrayan 1, we had no idea of how to really reach up to moon, and we wanted to just reach up to moon and find out, can we really travel such a long distance? And do we have a rocket, do we have engines on the satellite itself which will be able to guide us? Can we reach these signals, all that what I explained in the first part. So that was the idea of deciding on Chandrayan 1. So it was a very, very small, not a very large mission, but we were the 6th one in the country, in the world to really think of going right close to the moon. Now there are many other countries who have gone near the moon, but not landed on moon. And we also have parallelly other programs which are already in a very advanced stage called as a Gaganyaan, where we are going to take our astronauts into the orbit and bring them back successfully. So one of such maiden missile, the launch vehicle will happen sometime in February or March of next year 24, when we will take a dummy capsule which is actually going to have the human beings inside it. It's like a mini aircraft which will be taken into 800 kilometers orbit. It will remain there for 3 days, and then it will come and safely land onto airport near Bangalore. That's the plan what we have planned. And this is a starting of what Neil Armstrong did many years back, and we want to have our own astronaut also going successfully and landing onto the moon. But the first mission was to just go there and see, can we reach up to the moon? Is that distance we can travel it? Now if we have to travel such a long distance, and if we don't have that kind of a powerful engines, or we don't have weight carrying capacity, how do we plan it? So once again these scientists, they really came forward and they decided that let us use physics to our benefit. Can we bring physics and maneuver this particular launch vehicle or a Yan to the moon? Can I draw something here? simplistic I have drawn, not very complex. There is a launch vehicle which is on the earth and we are going to go to a moon. It's going to take time. We have a very powerful rocket, a powerful satellite carrying, more payload carrying capacity. Still 3,84,000 kilometers is not going to be achieved in 1 hour or 2 hours, the fastest. Americans have taken 4 days. So if I take simplicity, even the 4 days are required, the moon is not going to be here. By the time the moon has moved some distance, let's assume that moon is going to come here. If we are going to take 35 days as we are taking it today, maybe moon has longer distance, it has come here. So now what is the shortest path? Should straight like this. So these are all the issues which were discussed first. But what is important is that if we travel under power, then huge fuel will be required. Lot of fuel will have to carry in our yarn after the launch vehicle puts it into orbit. And we don't have that. We have, just for simplicity I am saying, if you have to travel 4 days, you require 400 kgs of fuel. Whereas if we go from here, our scientists calculated that we will be able to do it in 4 kgs using simple principles of physics. And it was something new for even the other scientists, the non-physicists, to understand as to what is their planning. So our plan, first you go, then we launch into this orbit, which is on one side plus 30,000 kilometers, 30k, and here it is only 200 kilometers. On improving this orbit, and make it circular as possible. So when we are firing here in that entire round, which I said, when the satellite is at 800 kilometers, it takes 5 rounds in a day. As it goes up at 36,000 kilometers, it takes exactly 1 day. That's why it is geocentric. It doesn't move. If it is launched over India, maybe over Mumbai or Chennai or Delhi or something, it will remain there only. It will not move. And if it drags, there are small thrusters on the satellite. No, satellite showing you that we can put small liquid engines . So this is your fuel, this is oxidizer, and the pipelines are being connected to all this, and you decide which thruster, which direction you want to fire it. But if you keep on firing, these tanks are limited. As I said, the when it was done, it was told to the chemist and the physicist that give you maximum 4 kg capacity for fuel and oxidizer. Now in 4 kg, if Americans are using 3 kg and we have to manage it, that was the biggest challenge. This came out with that you give a small impulse, at a time only 0.2 kg you fire it. Right location, either at this location or the extreme location as it is moving. That means you are giving a tangential velocity. Don't fire. As it will get a tangential velocity, the centrifugal force will increase. As the centrifugal force will increase, its own the satellite is going to get away from center point. Here is red. So fast it will stand. If you loosen it, it will come down. the way they spent only 0.2 kgs, and so far I think 7 manuring has happened. If you see on ISRO's site, today is going to be 8th or 9th manuring. I am not tracking it if you have. And so that means we have spent so far from this 4 kg, 0.2 into 9, or for simplicity let's take, so it has, how kg fuel has been consumed. Now how do we travel? Because this distance 1,000 or 38,000 kilometers. We have to travel from wherever it is going. As I said, equilibrium point they have reached. During this 1958 is being reached. To reach it was like आपण गोफण म्हणतो ना, गोफण किंवा बेसकी. गोफणीत काय करतो आपण, दगड टाकतो, गोल 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 फिरवतो आणि सडनली सोडून देतो. सोडून दिलेला दगड त्या गोफणीच्या बाहेर किती अंतर जातो बघा. त्याला कुठे नंतर एनर्जी असते. गोफणीत असतो तिथपर्यंत आपण एनर्जी देत असतो त्याला, पण गोफणीतनं बाहेर पडला की तो स्वतःच्याच त्याला एक्झिट व्हेलॉसिटी जी म्हणतात ती जी दिलेली असते त्याला, त्या व्हेलॉसिटीवरनं तो ट्रॅव्हल करतो. सो दॅट इज व्हॉट thrust. So the what they did 0.4 or and that extra velocity was given from this velocity. Now why that happens? Why our stone गोफणीतनं टाकलेला जास्तीत जास्त 200-300-400 फुटावरती जाऊन पडतो. 3,84,000. I suppose 60,000 kilometers it is going to go. So how it is going to go? Because of the earlier conditions which I explained it. there is a soft landing. You don't want Yan to go and back onto the main surface. It is soft, for example, like that. More than 25 different thrusters have been put onto the supply, depending upon adjustment. Land onto the surface of the moon. Now what happens when you are trying to land? There are 3-4 major sensors. I mean, there are Chandrayan, you will see more than hundreds of sensors are being put there, and those weight is a kind of a mandatory weight which you have to carry it there. But just for our simplicity and understanding, we will assume that only 3 sensors are there. The first sensor is going to tell us what is the temperature there. The second sensor is going to tell us what is the height from the surface of the moon, and the third sensor is going to tell us is there any area which is like आपण चिखल असेल किंवा hard rock असेल, so that kind of a area it is required to be sensed. So these 3 sensors are required, and it is going to do that last maneuvering, the best spot to land. We don't want very soft where the entire thing will go चिखलात अडकून बसलं तो rover बाहेरच येणार नाही. We don't want very hard where it may have a bumpy effect, and shock absorbers which are given there, they may not work on that very hard surface. So selection of that soft and hard is going to be the first challenge what Chandrayan 2 had. The second challenge is, if we are getting reduced our height at a very rapid speed, a flight when it takes at 2-degree angle only it lands. It cannot land vertically. If you have to land vertically like a fighter aircraft, you have to have so many other features into your system, and plus a very high risk. In a fighter aircraft, all these are deliberately added because we want that kind of a maneuverability. We want pilot to really escape in case of emergency. But a passenger aircraft, a civilian aircraft cannot take more than 2-degree inclination for landing. Those kind of a sensors will, the best sensors are used in the civil aviation, because in a fighter jet, I am not saying that if one person dies it is okay and 1,000 people should not die, nobody should die. But the responsibility is on the airline to make a safe landing. And when they are carrying 100 passengers, 200 passengers, there is a federal aviation agency, like we have a DGACA, lot of rules, regulations are required to be followed. And the best sensor what they are using today permits only 2-degree inclination to happen for landing. So you see a runway far away, and there you come exactly in the same line of the runway when you are going to land, and then start slowly descend, so that after almost 8 to 10 minutes from a height of 1 kilometer you land. So 1 kilometer, the last portion and the takeoff also has to be at 2 degree. But all these sensors to give a correct guidance to the pilot or the autopilot which is there on that system. Now similar system is required for this yarn also. It has to land. There is no fixed runway. So he has to choose the right location, maneuver himself, go there and make a soft landing on the right surface. So all these things are when are required, it has to have. And there is a possibility now, exact thing, even if I know, I don't know it first of all, but even if I know, I cannot share because that is something a secret which ISRO and others will not like to do it. So whether the hard rock was selected by a sensor or whether we had a sensor which was giving the height that miscalculated or stopped working, or the temperature which was required to be properly noticed, so that how much time the thruster has to be fired. If you fire it more time, it will get overheated and it will burn itself. The engine will burn. So all those calculations were required. But the second Chandrayan, even though as I said earlier that from 100 meters we lost the contact and then suddenly we realized that it has crashed after a few seconds. Now we have got all the data. Fortunately, all our sensors, even though it was crashing at that high velocity when it was falling down, they got all the data which was required. So we are well equipped now. We have well equipped because our Chandrayan 2, which was orbiting and still orbiting, has taken more number of photographs, and we have selected the best region on the South Pole, the best location to be done. So we are more prepared for which land and which area where we are going to go. We cannot go into a crevice, a valley, we cannot go onto a hilltop. So a pathar म्हणतो तसं पठारावरती आपल्याला जायचं आहे. So we have selected the right table on which we are going to land. We have selected the right spot. We have selected the right velocity. The Chandrayan 2 had this orbiter. Chandrayan 3 doesn't require an orbiter. So almost 400 kg extra weight we could bring from that orbiter, which is not required in this because orbiter 2 is still working. It is giving help to the current Chandrayan 3 also and will continue to do it. It has a lot of still life. Another at least 2 more years the Chandrayan 2 orbiter is going to orbit and keep on giving the data which is required. So all that 500 kg has been used in stiffening our legs, the 4 legs on which it is going to land. So more stiffening has happened there. As I said earlier, Chandrayan 2 didn't have this 880 kilonewton. We are going to have 880 kilonewton which is going to get fired and apply the brakes to this particular satellite. So everything looks today with whatever data, whatever assumptions we have done or revalidated these assumptions from Chandrayan 2 has happened. And now, as we discussed, we have come to a stage where it has crossed this and entered into it. Once again, it is going to be the elliptical circle which is going to come, and 200 kilometers we are going to start orbiting. A perfect circle is not possible, but near perfect circle is being attempted to bring this 200 kilometers and revalidate all the assumptions again. So that will happen tomorrow, day after tomorrow, in next 1 or 2 days. Signals will keep up and down. The scientists will verify all this data, what has happened, and then they will decide how to go. The downward path from 200 kilometers to this also is not straight like this. It will crash here. So same way it is going to happen. आता चकली बनवणार आपण जेवढ्या चकल्याच्या आपल्या हे करता येते तेवढं करून finally we are going to land on it. So how many rounds in that chakli we have to give, that will get all this calculated. So it may be the time covered will be in next 9 days or 10 days. So 23rd or 24th, all that will come to know in next 1 or 2 days after all these calculations and the revised trajectory is being fixed onto it. Now once it lands on the 4 legs, which is going to have a lot of bumpiness, because all the trials of this lander we have done on a simulated moon at Bangalore. A huge laboratory has been created. A few years back there was a theory that Neil Armstrong has actually not landed onto the moon, but he has just photographed onto this simulator which was there, and America claims that we have landed on moon. And then the Russians has to challenge, and then a lot of things, and then the flag is moving this side or wind is there, there is no wind, all those theories which came up, and finally it has been concluded that yes, Neil Armstrong has really landed. Russians have also landed later on. Many other countries have attempted to land it. Nobody has been successful so far onto it. China also is not successful. But soon we will be, after this Chandrayan 3, we will be taking those further missions. As I said, Gaganyaan is the attempt which is being done. So what we are going to do is, after the lander now lands, and it is expected, like normal, when the ball drops down, it doesn't stop immediately. Chote chote tappe khat, finally the physics says that finally after some time it is going to come to a rest. Now because the gravity is 1/6 only, we are expecting, or the scientists are expecting, that it is going to have more number of jumps than what it has taken on the earth when we have simulated. So we are going to give kind of a cool off time, that let it go, land, and then keep on jumping, bouncing. Finally when it settles, within the shock absorber also there will be some spring movement. First what I said is jumping up and down from the surface of the moon, but now finally it has taken a firm seat. Still the rest of the body on the shock absorbers is keep on jumping, and when that will come to a rest, that is where the cool off time is going to be over. Now if there is a delay of 1 day, that means 23rd goes to 24th, as I told earlier, we have a window of only 14 days because we want our solar panels to get opened, and 14 days is a daytime on the moon. So the 14 day will be available now only 13 days if we land 1 day late. So that is where all these calculations, right from here to go on to this and still achieve. So we have chosen a day, 23rd or 24th is when on the south pole there will be sunshine. If there is no sunshine, our solar panels will open, but they will not get a sun. Now we are expecting that, like we have a cloudy season, there is no sun, so you are not going to get energy what was expected. So the similar situation happens there. Once again, the solar panels will not generate the sufficient electricity or the energy which is required. So all those ifs and buts are there, which are going to get clarified as the things will happen. Because we are not able to predict what is going to happen after 2 years, whether it is going to have a rain or no rain here on the earth. How do we expect that ISRO will be able to do it? Now we have generated a lot of algorithm. Our predictions are becoming more and more clearer and better. What was earlier being forecasted by doing only a small experiments, today the satellites and other ground stations put together, we are able to do a far better prediction. So when this rover is going to come out, and after 14 days, even though it cannot move now because it requires more energy and we have a limited fuel, every day when I'm talking every day on moon, that means after every 14 days on earth, the solar panels will still be operational. So the whatever equipments are being operated out of battery, so at that location, if it can move little bit its arm or robotic arm and do experiments there, or keep on doing a video shooting for the next 6 months, 1 year, 2 years, we are still going to get the signals. So that means, like Chandrayan 1 and Chandrayan 2 has given, Chandrayan 3, after the 14 days of experimentation is done where it is going to have a live communication, our contact is not going to be completely lost. We are not able to move that now. We are not able to do any major experimentation on that. But the cameras which are going to get powered with solar, other sensors which doesn't require much of a power, which can be operated over solar, a weak signal still can be sent from that solar generated power to earth. Earth can still send a signal. There is an antenna which can receive that signal with that small energy what solar is going to do it. So mission is not going to be over after 14 days. Mission will continue, like Chandrayan 2 mission is still continuing after so many years, and Chandrayan 1 also, whatever the pod what we have put, it is still radiating, it is still giving something. And if all this data which we are going to collect from 1, 2 and 3 will hopefully make us capable, to think of a manned mission by the time if the Gaganyaan, the re-entry, most important, like re-entry on moon, we are demonstrating that we are able to land on moon, so why we cannot land on earth? So instead of landing on earth, first itself we have taken a opportunity to land on moon. Of course, there is no human, there is no other safety precautions which are required. At the most, our Yan will get crushed like Chandrayan 2, which will not happen surely. I am so confident that so much of discussions, deliberations have happened, lot of efforts have gone after Chandrayan 2, lot of simulations, lot of imagination, stretch of imagination has happened, and we are far equipped. Probably ते एकदा भाजलं की आपण जसं हे करतो तसं we have over designed this time, that 300 additional kg which we couldn't get could get because there is no orbiter required, and orbiter still continued. If the orbiter also would have crashed in that Chandrayan 2, once again the orbiter is required. The signal is not directly going to come from the Yan. Yan has a limited signal. So that Yan is going to give a orbiter which is at 200 kilometers orbit. And that 200 kilometer orbiter is going to communicate. So it is going to be kind of a hooping, what I said, is already being done on moon. Directly Yan to communicate on a ground station on earth is impossible. So Yan will communicate to this orbiter at 200 kilometers. Once again, it is not a geosynchronized orbit. So Yan is going to collect lot of data, and as soon as it sees our satellite there, it is going to push all the data. Then when the satellite sees best location from moon to earth, it is going to push that data to back to us. So it is no more now 3 plus 3 plus 3 seconds. It is going to be far larger. And since we are on the south side of the moon is not easily accessible from the earth. So the the orbiter has to come towards the north to see earth. Then only it can see earth. And then we should have our own location. Earth also is moving around its axis. So when moon is being seen, like we have Amavasya, then moon is not being seen for a different reason, but similar thing happens. I am giving that example, that even if the satellite is there, we are on the other side of the earth. Currently America is here. So we have agreement with other nations. There are 5 such 30, 34, 36 meters antennas which are there in the world. So any antenna which is going to catch a signal from us, and those countries have agreed, and we also extend our antenna to other countries whenever they have their missions like this, and we give that data. So there is an international agreement. So wherever our antenna, of course, that is all encrypted. We don't want them to understand what data our satellite has given. So from that antenna through geosynchronized one, it will go once again to geosynchronized and will come to our geosynchronized antenna here. It's a huge, I mean, if I go on elaborating, you will go crazy. That much of times the waves are going to move from one location to other location to finally reach up to our Hassan, where we have a master control facility, or near Hyderabad where we have a processing. All this encrypted data will come to National Remote Sensing Agency, where it will be once again converted into something what our scientists will be able to do it. Once again, when it has to go back, it will go to Hyderabad after the scientists and astronomers who are sitting. It will get encrypted. From Hyderabad it will go to maybe a Delhi or somewhere, and from there it will get this one if it has to go through some other antenna. Fortunately we are in front of moon that time, our Bangalore facility itself can directly transmit. So like that, all these difficulties will be overcome. I think the next 10 days are exciting for ISRO to really ensure that it is going to land. Next 14 days are going to be exciting for all of us, because we will be able to see lot more better clarity of the moon, lot of data which is going to get analyzed, and subsequently as this rover and lander are going to be stationed there and still have a short span of every 14 days to operate their solar and generate energy and communicate back to us. I think huge data is going to be generated in the next few days, months, years, and the next missions will be planned. So with this I stop here. I hope you enjoyed, didn't get bored. Thank you very much once again for giving me this opportunity and sharing. It is not only for me to be good, But I think all these efforts what ISRO is taking has to be communicated. So whoever calls me, whatever I can share, I always do it. Anytime you call me, I will be happy. But this has to get percolated. Many of us, we don't know what exactly are the challenges. Blaming, criticizing ISRO or government is very easy, but the efforts which are going beyond it are so stupendous. It's unimaginable, unimaginable. Volumes and volumes of thesis have gone into the ISROs. I mean, they have something like this 100 rooms where handwritten data is stored. Even though the electronic industry is there, we are worried. We are still having both the data storage, excellent library, and most important in that library is that you give any keyword, within few minutes you will be given a rack or the room of these 100 rooms, which room you should go, which rack, and where that particular the data or the thesis has been filed, or the report, the file note as we call in the industry, has been filed there. So that's the way ISRO is operating. Similar exciting stories are there. Whenever opportunities will come, I will talk about Dr. Kalam and the BrahMos missile. That's a very, very interesting story similar to this, which I will be happy to share. Not that I am giving you opportunity to invite, but I am part of the CCS. It's my responsibility also to communicate. So with this, once again, thank you very much, and thank you all. All the best.